Now we go to the problem of computing the length of the a curve, a rectifiable patch. Okay. So this lemma gamma is a C1 map. A C1 map is different from a smooth parametric curve. C1 map means that this gamma is differentiable in the closed interval AB. Okay, this is C1 map. What C1 map means? Well, our smooth parametric curve is continuous in the closed interval AB, but it only differentiable on the open interval. Of course, we require that the derivative is bounded. Okay, but it might not be differentiable at the endpoint of the interval for our parametric curve. But for simplicity, we first prove this case slightly stronger assumption that our gamma not only be a parametric curve, it also differentiable at the endpoint. Then we have a derivative function defined on the closed interval AB, which is continuous. So this is what C1 here means. That is, gamma prime is defined on the closed interval is continuous. Gamma prime, the derivative is continuous. This is just the meaning of C1. Okay. That is, the C1 curve here is slightly stronger than the smoothness of the parametric curve. Smooth parametric curve does not require to be differentiable at the endpoint of the interval. But now we assume that this is also differentiable at the endpoints, at the two endpoints. Okay. Now, such gamma, of course, is a smooth curve, right? The assumption on our gamma is stronger than the requirement of a smooth curve, because not only all the requirement of a smooth parametric patch, we also have the differentiability at the endpoint AB of the interval. Okay, so this is a smooth parametric curve, more than a smooth parametric curve. So it is rectifiable. And the length is given. The length by our notation is L gamma is the integral. Okay, so for smooth curve, the length is easy to compute using integral. Okay, so this is obviously very important. Now we prove this result. Suppose P Ti I from 0 to M is a partition of AB. This is a partition of AB. How final? How many points? We don't care at this moment. We will make it clear later. Then we estimate. So we have a curve. And we have a partition of the interval AB. Correspondingly, we get some point in the interval. Those points are the gamma Ti. Okay. Then we estimate the length of the inscribed polygonal. That is joining the points. We get a polygonal, and the total length of the polygonal we denoted in our notation. This is L gamma P. So we estimate the absolute value of the difference of this, which is the integral. Okay, if if for any epsilon positive, we can find delta, so that if the gap of partition P is less than delta, then this absolute value is less than epsilon. Then we are sure that gamma is rectangular, and the length of gamma is precisely this integral. Okay, this is the definition of length of parametric path. Okay, so how to do this? By definition, the first term is I from 1, gamma ti minus gamma ti minus 1. So this is gamma ti minus 1. This is gamma ti. So the this gamma ti minus gamma ti minus 1 is this segment or this vector. So its norm is the length of this segment. Therefore, the distance from gamma ti to gamma ti minus 1. Okay? And the second term I copy. How to estimate this? Obviously, we can divide the integral into pieces. We use this fact. AB equal the sum ti minus 1 ti. We use this well-known summation property of integral. So this can be rewritten as ti minus 1 ti. We replace the integral variable by s. Okay. Then this gives us this copy. I use the dot. In our this formula, I use the dot to denote the derivative with respect to t. This is prime, but we will make square. So if you use prime, the place to put 2 in the square will be occupied by the prime. Therefore, I prefer to use dot to denote the derivative. Okay. So go back to our estimate. In this integral, we can apply the mean value property of integral. This integral, because the gamma prime is continuous, the norm of gamma prime s is also continuous on s. Therefore, by the property, mean value property of integral, we have a c in the interval ti minus 1 ti, such that this integral equal the integrand at the c. Then multiply the length of the interval, where the c is a point of the interval ti minus 1 ti. But for every I, the c might difference, so we had better denote this by c I. Okay. So we have right. So to continue our argument, we estimate the ith term of this summation. So we estimate this in the next page. Gamma ti minus gamma ti minus 1 minus the norm of the derivative at ci multiplying the length of the interval. Okay, what's this? We want to apply the mean value theorem to get gamma prime c I eta I maybe. Then ti minus 1. This is a good idea, but we cannot do this. This is not true because gamma is a vector valued function. If gamma is real valued, n equal to 1, one-dimensional function, this is okay. This is precisely the Lagrange mean value theorem. But for vector valued function, we do not have Lagrange mean value theorem. Because for each component of gamma, the mean point might be different. You cannot use a single eta I. Okay. Of course, we have the mean value inequality. This is not true, but this is true. The mean value inequality is true, but this is not useful for our purpose. Okay, we cannot use this. Using this, although it is true, it does not help our argument. Okay, so what should we do? We need to go into the object inside, more involved this argument. How to estimate this? So this is a norm of the vector. We suppose gamma, the component of gamma is gamma 1, gamma n. Gamma is a vector valued function. It has n components. So we need to go to the working with components. So, this is the norm of the vector. So the norm of this vector, gamma ti minus 1 is a vector or a point in Rn. So the norm of this point is the square root of its component square. Component is gamma j ti minus gamma j ti minus 1, then square. This is the norm of gamma ti minus gamma ti minus 1. And also this is also a norm of a vector. We also write it in components. So subtract square root of j from 1. Gamma j dot ci square. Then multiplying ti minus 1. Okay? Now for this, gamma j is the jth component of gamma. So we can apply the Lagrange mean value theorem because now it is a real valued function. This can be written as gamma j dot in the middle point between ti minus 1 ti. So this point, of course, might be denoted by eta I. But for each component, it is different. So it also contains a label j, then square. Then ti, maybe I will change the color. ti minus 1. Okay? Applying the Lagrange mean value theorem to the red circle part in the previous step, we will have a ti minus 1. I write it here. Gamma j ti minus, maybe I write in the very end. Gamma j ti minus gamma j ti minus 1 will be gamma j prime eta ji ti minus ti minus 1. But when you take the square, then take square root, they sum up and take square root with respect to j, the ti minus 1 square can be moved outside the summation, then outside the square root. Okay, so this is why this become this. This is the reason. I cannot write every step. So the next term will copy. Okay. Now the ti minus 1 is common. We can collect them together and add a pair of we can do this. Collect them together. Move the ti minus 1 out, and resolving the difference of these two square root. So what's this two square root? This two square root is easy to deal with using geometric method. So this is the origin. This is a point which coordinate something. So the square root of ai square minus the bi square. What's this? The first term is the distance from ai, a1, a2, an, from the point A, not ai. ai is the coordinate. Maybe yes. So this is the point A, this is the point B. So the first term, sigma, the square root of sigma ai square, is the distance of A to the origin, right? And the second square root is the distance of B to the origin. The difference of these two distance will not greater than the distance between AB. Triangle inequality. Okay, using this result, go back to our estimate. The difference of the two square root will not greater than the square root of gamma j dot eta j I minus gamma j dot c j, then square, then copy the ti minus 1. Okay, this is a very crucial step to estimate the complicated difference of the two square root in the previous step. But using this geometric idea, it is quite easy. Okay, now having obtained this inequality, we can go further. Maybe I make something wrong. 可惜 I not 可惜 j. The index here is not true, right? Oh no. This is 可惜 I. So this is Ci. So this is also Ci. Then Ti minus Ti minus 1. Okay.